This card was released in 1987. It was so popular that it was cloned, so impressive that it was thought to be a new standard, and so influential that it created a new market of hardware. This card was the first GPU for PCs to actually make a meaningful impact on the market. So why is it that no one ever talks about this thing? This card is the IBM 8514A. It was announced alongside the introduction of the PS2 line of computers and made it to market just after they launched. It was a totally optional card that most PS2 users probably never even knew existed. It was targeted specifically at high-end workstation users and really needed the matching IBM 8514 monitor to fully utilize it. That display was much maligned by reviewers at the time though, and that's just for being blurry, which isn't even the worst part of it. But some of that can be forgiven since this was literally the first VGA add-in card ever made. On that, being for PS2s means that this is kind of weird. This slot isn't PCI, it's not ISA, heck, it's not even eISA or VLB. It's microchannel, and unique microchannel at that. It can only be installed in one slot on the motherboard that was essentially designed specifically for this card. So why on earth would anyone want to put up with all of that just to use it? Because of this. The 8514A contains a coprocessor designed to offload drawing from the CPU. It accepts commands from the CPU to directly modify the frame buffer on its own, freeing up the CPU to do other tasks like load more data, which massively speeds up graphically complicated programs. This was mostly targeted at CAD users. IBM was even working directly with AutoCAD for the development of the drivers. Now, this wasn't actually a new concept, even to IBM. The 8514A was a successor to their PGC system, which was released alongside EGA in 1984. But that had a lot of downsides and was extremely expensive and complicated. It was essentially a whole second PC on the card, including the 8088 CPU that could be the same as your main processor. The PGC was $3,000 and non-negotiably required the $1,300 5175 monitor. So the 8514A seemed like a bargain, costing only what the PGC monitor did and technically did not need to be used with its bespoke display. The downside was needing a PS2, but even if you could plug it into a non-PS2, it would be useless. The special slot it goes in passes through video from the onboard video card because the 8514A doesn't have or emulate the Motorola CRT-C chip needed for standard PC video cards. But this card made such a splash that it wouldn't be a problem for long. Let me give you an idea of just how influential this card was. It's the only accelerator listed by different programs, like Microsoft's series of entertainment packs or Quarterdeck's Desk View X. If you were smart and installed Windows 3.1 from your hard disk, the first file from the first disk you would copy is the driver for this card. And Word for DOS even supported a special high-resolution text mode right out of the box with it. But Word shows where this card becomes something else. This card is a GPU, but it has another party trick up its sleeve: higher resolutions. The PS2 computers were the introduction of VGA, a new analog video standard. Unlike the previous video signals for MDA, CGA, and EGA, VGA was designed with room to grow. For example, onboard VGA was only capable of displaying up to 16 colors from a palette, but the 8514A could display 256 colors, and had a memory expansion to do that at higher resolutions as well. The grayscale scanner I reviewed could get up to 64 levels of grayscale color depth, and something like PC Paintbrush 4 can remap the colors to have more useful values for your image. Another way VGA was future-proof was by using the ID pins on the connector to communicate what kind of monitor you have connected to your card. These aren't like modern EDID. The pins are treated like jumpers and are just grounded or floating. For the onboard video, this would most likely be used to tell if you had the monochrome 8503 monitor versus a color monitor like the 8513 here. But those pins could also indicate the maximum supported resolution for the display, and the 8514 monitor was capable of showing up to 1024 by 768 in 1987. Although with one drawback: it was interlaced and slow at effectively... I'm gonna stop myself right there because I found better information after writing the script. The official vertical refresh rate is 43.48 Hertz according to the IBM technical manual. Yeah, it's really slow. Interlaced means that it draws half of the horizontal lines per vertical pass, alternating between the even and odd fields. This technique was brought over from television, but broadcast camera feeds are more likely to have visually similar lines next to each other. The artificial computer graphics being dealt with here are much more likely to have unique lines that will end up flickering from the interlacing. Now, I don't have the original 8514A monitor. Everyone hated it, and I suspect a lot of them were dumped early on based on the reviews that complained about it even at launch. I do have a Philips Magnavox CM2015 from a little later though, that can still display this. As an aside, so far all of the LCDs I've tried either fail to sync at all or would get the odd and even fields backwards with no way to flip them. I'm capturing this using a RetroTink 4K, but I had to make a completely custom mode line and profile for it. Normally, using a CRT is always better, but it's hard for me to convey just how awful this can be to use, particularly when there are black and white grids on the screen, and the entire display just seems to flash so bad that it is literally unusable because of the interlace flickering. The 8514A was trying to hit some pretty lofty goals with its resolution and price, and made some pretty big sacrifices to do it, but not everyone else was, which brings me to these. The short-lived time of Super VGA clones. This is a Trident 8900C. It's a little later and a little dead, but this was part of a market of Super VGA cards that exploited the room between the standard VGA onboard output of the PS2 and the 8514A. To avoid interlacing and having to render as much directly on the CPU, these cards added a new resolution option, 800 by 600. This was only possible because IBM made VGA so dynamic to support the 8514A. Of course, none of IBM's own displays could show 800 by 600 though, which led to the clone market creating their own displays. But without a guiding light from IBM, this became a mess. If you've watched my video from years back on how VGA works, you might have an idea of why. VGA uses horizontal and vertical sync pulses timed between lines being drawn to the CRT to tell it when to shut the beam off and move it back. The timing of this was very critical though. If you send your horizontal pulse earlier, the image moves right. Conversely, if you send the vertical pulse later, the image moves up. And if you have an industry create a new video standard without consensus on what these timings are, each card will pulse at different times and the video will be somewhere completely different between every card. Monitors still used fixed analog potentiometers for moving the image around, which meant your image position could just be different between resolutions, or the monitors could just not be compatible. For example, the Magnavox can sync to the 8514A and can show the input just fine, but it puts the image all the way over to the left, and I have to max out the horizontal position and shrink the image size down just to be able to see the whole thing. This was happening across the entire industry and was quickly going to become a massive problem. So after IBM shunned all of the clone companies with the PS2, they decided to take the future into their own hands. And in 1989, the VESA Standards Group was born. Their original goal was to create a list of predetermined VGA modes that defined timings for how sync pulses should be sent. This group would go on to solve this problem eventually, but without IBM leaving the VGA spec so loose to support the 8514A, we may not have had VESA. Now, these Super VGA clones were very basic. They just copied the video capabilities built into the PS2. This gave people nicer, higher resolution displays than CGA or EGA, but the hardware level graphics capabilities of the 8514A were still exclusive to the PS2, since IBM only made it for microchannel systems. At least until ATI came along. ATI had been making a name for themselves with their VGA Wonder line of cards after the launch of the PS2. These were well regarded, but still just another VGA card. But in the background, ATI was working on something more. And in 1990, they announced that they had created a clone of the 8514A coprocessor that they dubbed the Mach 8. As an aside, ATI would continue the Mach naming on to the 32 and 64 cards, but the original Mach 8 was never publicly marketed as that. Now, they released two graphics cards using the Mach 8, the 8514 Ultra and the ATI Graphics Ultra. The 8514 Ultra was a cheeky card compatible with both PS2s and PCs, with MCA and ISA connectors on either side of the video card with a video out daughter board that was movable between ends. Elsewise, it's functionally the same as the IBM card. The other one is different though, and I managed to track down one nearly complete in the original box. The Graphics Ultra is quite a significant card. It combines standard VGA functionality and 8514A compatibility into one card, but also integrated a bus mouse port and included a mouse. This made it nearly a PS2 upgrade card that you could drop into your likely clone PC and be ready for graphical applications. It also fixed the major flaw with the IBM 8514A by allowing you to output 1024x768 in progressive scan, eliminating the flicker issue. Now on the original 8514A, if you run a program that only supports 1024x768, but have a 640x480 monitor connected, you will see it crops the output to just part of the frame buffer. The 8514A was always storing the full image in RAM. IBM just didn't put a good enough RAM DAC on the card to have full bandwidth. ATI did, but you would have to change your supported resolutions by rewriting the card's EEPROM though. There was no standard way to change graphics resolutions in DOS, so they just did the lowest common denominator option that would work. Now, these low-level upgrades over the IBM card were possible because ATI fully cloned the 8514A at the hardware level, and they were the first company to do so.
Actually, maybe not. I found claims that Western Digital was selling them a few months earlier, but ATI was the clear clone leader and lasted a lot longer. The Western Digital card apparently had exceptionally bad AutoCAD performance and poor support for Super VGA features, which probably made it less appealing.
This was a much harder feat than cloning previous IBM hardware because IBM did not publish hardware-level documentation of how the 8514A worked, most likely to prevent clones. Instead, IBM included a software driver that the developers were intended to use. This was known as the application interface, but was shortened to AI. Let's get this out of the way. Artificial intelligence was already a concept that people were talking about at this point. Here's a Byte cover story from 1981 about it. This was just a coincidence. Now, right before the ATI card was announced, PC Magazine was talking about how hardware manufacturers may offer 8514A compatibility, and actually, this was a hot topic for a while. The newly formed VESA group was even planning on creating their own standard for it. ATI kinda jumped the gun on this a bit with their clone though, because it was a complete coprocessor clone. Their reverse engineering was so precise at a hardware level that you can use IBM's original adapter interface software with ATI cards, and there's a funny thing about that could have happened, but didn't. ATI also had their own version of the adapter interface software that was included with their card, and it was backwards compatible with all software targeting IBM's card, while providing access to ATI's new features. IBM's fear of having the card be cloned accidentally created an easier way to clone the card by simply re-implementing the software instead of the hardware. There was almost a future where hardware graphics APIs for PCs weren't DirectX, OpenGL, or Glide, but started with IBM 8514A AI compatibility.
Actually, while doing some final bits of research, it turns out that the Appian Renegade had an 8514A AI emulation driver. But this was the exception to the rule, mostly because going through the AI on IBM cards was extremely slow. Once hardware specs had been figured out, software started driving the hardware directly. And this problem is biting me in the butt now. I wanted to show a performance difference between direct VGA and the 8514A in AutoCAD, but with all of the sample files, the 8514A with the AI is actually slower than the CPU drawing. Perhaps a 286 PS2 would benefit more, or more complex files may have shown some more improvement, but comparing the performance of this card was extremely difficult even when it launched. Some magazines resorted to creating custom synthetic tests. Others relied on third-party tests, one claiming that the 8514A could do 1 MIPS compared to the TI TMS 34010 doing 1.2 MIPS. But then another article claimed that the TI chip was 16 times faster in AutoCAD than the 8514A, which is probably because of the AI. This was bad enough that third-party AutoCAD ADI drivers became available to bypass the AI, claiming to get 15 times the performance, which kinda tracks with the other tests. Now, through sheer luck, I managed to find a demo version of this exact driver, which lets you see the performance difference. As a benchmark, I'm rendering the menu tree file with redraw here to only redraw the data already stored in RAM. The AutoCAD VGA driver does it in 6.47 seconds, while the AI driver takes 21.1 seconds. The Panacea hardware driver, though, is 1.07 seconds. If you blinked, here it is again, but also with 1024x768 rendering, which only bumps it up to 1.14 seconds. Going direct to the hardware makes a massive difference. The IBM AI software was so terrible that the clone companies were working together to form their own standards for register access. IBM even realized how terrible this was, and the successor to the 8514A, the XGA card, was going to have open hardware information available to drive it. But this was too little too late, and the clone companies were already running away with the market. And IBM's competition took it in a different direction that ended up being wildly more popular.
Bonus section! If you went into this video knowing about the 8514A already, one of the things you may have heard about is that it requires an 8514 or similar monitor, because 1024x768 interlace is the only thing it can output. Even IBM says that in one of their later tech bulletins. But this is not true. The 8514A directly reads the ID pins on the original IBM PS2 monitors, and the AI software automatically communicates to supported resolutions it can run at. For example, here is AutoCAD R11 on the 8514A connected to an 8513 running at 640x480, showing 256 colors. This was an intended setup, and it didn't require the RAM expansion. But if a program like Mahjong 8514 doesn't bother to read the monitor ID, then you're only going to see part of the frame. The bigger problem, though, is anything made after ATI leaked the specs that drives the card directly for speed ignores this completely and assumes you're running a 1024x768 monitor. And I'm pretty sure the official Windows drivers made that assumption as well. So software like DeskView X and Fractant can both overdrive and damage a 640x480 monitor. There is another quirk to this, though. The ID pins must be set for the resolutions to work correctly. I actually had to modify a VGA splitter for this project to be able to manually set them, because when they're free-floating, it defaults to monochrome 640x480. Also, the 8514A can do dual monitors, but I'm going to leave that for another video. Look out on my second channel for that. For now, though, let's get back to how this thing blew everyone's minds again. When IBM introduced the 8514A, they knew people would want to use Windows with it for some applications. I covered one such example with their publishing suite and scanner in a previous video. This meant they had to make Windows drivers for the card. However, these drivers were different and didn't go through the AI, and software running on Windows could no longer directly access the 8514A coprocessor anymore because it was being used to draw the GUI. As a result, no Windows software has ever been able to directly support the 8514A. But then, why do my copies of Microsoft Entertainment Pack claim to support it? Well, while no programs could use it directly, they all indirectly benefited from it, especially on Windows 3.1. Windows 3.1 was introduced during the 8514A clone adoption period and was designed to heavily lean on it using the GDI API, or Graphics Device Interface, which created a market for graphics accelerators. GDI created a standard way for programs to be developed for Windows to access graphics functionality of your video card. So the 8514A was able to improve the performance of GDI-based games like in the entertainment packs. And this brings us to the last of the big competitors. S3 had been working on taking the 8514A and adapting it to more specifically accelerate Windows. Unlike ATI, they sold chips to other vendors to produce cards, which is where this card comes in. This is a Diamond Stealth 24, which uses an S3 86C801. This is a second-generation chip specifically designed to work with Windows 3.1 and fully supported the new VESA standard modes and exceeds both the IBM and ATI cards in features. It is an evolution of S3's original 86C911 chip, which was partially based on the 8514A. The newer chip has shed some of its 8514A roots and is no longer register compatible. Instead of relying on the 8514A name like ATI, it was purely known as a Windows accelerator. When you install or reconfigure Windows 3.1, you have the option of providing a custom driver, which lets you set it up to know how to use your specific graphics accelerator to enhance its performance. Programs like the games and screensavers included with the entertainment packs could take advantage of the hardware through GDI, which translated compatible drawing commands through to the provided driver. Any Windows application could now be made faster by using GDI to take advantage of the coprocessor functions of any graphics card. This is true for the ATI Graphics Ultra and for the original 8514A, but the S3 card is much more powerful. For example, look at how fast SkiFree runs on it compared to the ATI in the same system. This is hardware accelerated graphics rendering on a PC in 1992. While the term GPU may not have been coined until later, these were absolutely 2D GPUs. More companies would start to join in on this, like Trident's T-GUI series of processors, and interfaces would improve to VLB and PCI. This is when PC graphics really took off. The 8514A brought more than graphics acceleration to the PC. It brought the industry together. Its video modes were standardized by VESA, its functionality was liberated by ATI, and Windows created the GDI API that abstracted it and its clones for anything to use. And GDI would evolve into DirectX, which is still used today. The IBM 8514A set all of that in motion. There were other GPUs like PGC and TIGA, but none of them rallied support like the 8514A, which is, in my opinion, one of, if not the most influential GPUs ever made. Well, if you enjoyed this video about a bit of technology history, you may want to subscribe to my channel to be notified when I release more. If you want to help support the channel, you can find me on Patreon. But for now, that's it, and I will see you next time.